Okay, hello everybody. A very good evening. I hope everybody's doing great. Just give me one more minute. I'll just download the PPT and then we will share the screen. Okay, now I can share my screen. Okay. So this is solutions chapter, right? Okay. Okay, fine. So the first question is the brass. For this. Okay, fine. So I say that the brass is what? As an example for what? Right? Now brass is an alloy, right? Right? And all alloys are examples for what?
Solid solution.
Yes, absolutely. Right? All alloys are examples for solid solutions. Right? So the answer would be A. Right? Next. 200 ml of water is added to 500 ml of 0.2 m solution. What is the molarity of the diluted solution? Now it's very simple, right? Now, whenever you go for dilution, what you have to understand is whatever is the number of moles of solute is not going to change, right? Only the volume is going to change, right? So in this 500 ml of 0.2 m solution, right? If I want to calculate the number of moles of solute, right? Now we know what is the molarity formula. Number of moles by volume in ml into 1000 in the numerator, is it not? So if I have to calculate number of moles, that would be 0.2. That is the molarity. I'll write it here. Okay, that would be 0.2 into 500 into 10 to the power minus 3. Now I am putting 10 to the power minus 3 because I want to convert into liters. This is there's 1000 here. Okay, that is the number of moles we have for the solute. Now this number of moles is not going to change, right? So now only thing which is going to change is the volume. Now if I want to find the new molarity, that is number of moles by volume of solution into 1000, new molarity is, sorry, the number of number of moles is this, whatever we calculated, divided by whatever is the total volume. Now already I had 500 ml, right? Now I'm adding more 200 ml. So now it is going to be 700 ml now, total volume into 10 to the power is 1000. And this gets cancelled. Again, you can calculate this and get the final answer. Okay. Right? So when you go for dilution, the number of moles won't change. That is the number of moles of solute won't change, but only the volume changes. Right? Okay, next question. In which mode of expression the concentration of solution remains independent of temperature? Which one? Right? In molarity, what you understand is molarity is number of moles by volume. So if I'm going to increase the temperature, what will happen to volume? Volume will decrease, molarity will increase. Right? Normality, again, normality is number of equivalents divided by volume. Again, if you increase the temperature, volume will change. That is, volume will decrease and the normality will increase. Right? Formality and molarity are same. Right? But when you go to molality, what we have? Small m, molality is equal to number of moles by mass, right? Mass of solvent. That's the formula which we'll use. Right? Now you see that when temperature is changing, the mass will not change, number of moles will not change. So molality is independent of temperature. Right? The molality is independent of temperature. The option is going to be D. Okay, right? Whereas all the other things are going to change with respect to temperature because volume term is there, right? Okay, next one. Increase in temperature on an aqueous solution will increase what? Okay, we'll see. Okay, increase in temperature of the aqueous solution will have decrease in molality. Obviously, now only we saw the last question, it is not going to change anything, right? And molality is independent of temperature. Decrease in molality, yes, we saw this, right? Now, molarity is equal to number of moles by volume. So if temperature increases, volume decreases, molarity increases, right? Okay, but molarity they're telling is increasing. Increase in temperature is going to what? Is going to increase my molarity. They're telling it is decreasing. How is it decreasing? If we are doing it entirely wrong. If temperature increases, temperature and volume are directly proportional, inversely proportional.
Inversely.
Right, directly proportional, right? When I'm going to supply some energy, the gas expands, right? Right. So temperature and volume are directly proportional. So if temperature increases, volume increases, molality will decrease. Okay. So yeah, this is the correct answer then. Right. There's going to be decrease in molarity. Again, mole fraction, only number of moles are there. Weight by weight percentage. Again, now only weight is there, mass is there. That is not going to change. Whereas wherever you have volume term, in that case, you're going to have some changes. Yes, tell me.
Sir, increase in temperature, will it generally causes like the molecules will escape out of the solution. So will
that depends on what kind of chemical species are you talking about, isn't it? Not all of them will do that, right? Even if you think about it like that, or even if you think in terms of that also, if you see, if I'm going to convert the solid particle into gaseous particle, again the volume is increasing only. Is it not? Right? But the number of moles of solid, for example, if I dissolve NaCl in water, right? Now, if I increase the temperature, the NaCl is going to evaporate? No. Right? So that is what you have to understand. Right? Okay. Next. Right. Molarity of liquid HCl if its density is equal to 1.17 gram per cc. What is cc?
Centimeter cube.
Cc is centimeter cube. So 1 centimeter cube is how many ml? 1 centimeter cube is how many ml?
1 ml, sir.
1 ml. Okay, this you have to remember. Okay, when I give 1 gram per cc, I'm talking about 1 gram per ml. Okay, right. So now you have to calculate molarity. So molarity we know is number of moles of HCl divided total volume of solution. If it is in ml, we will put 1000. Right. So now if I have to calculate the number of moles. Now density is given. Right. Density of the solution is given to us. Right. Now you see it is liquid HCl. Please be very careful. It is not aqueous HCl. Right. That means in this I'm going to have only HCl, no water. Right. So be very careful here. Okay. So here if I say the volume of solution, that is nothing but the volume of HCl only, because it is not a solution anymore. It is just a liquid. Okay. So number of moles by volume of solution we take, right? But in this case, volume of solution nothing but volume of HCl only, because it is a liquid. It is not a solution, right? So now what do you understand from this statement? From the density being 1.17 gram per centimeter cube, can I say 1.17 gram of HCl is there in 1 ml of HCl? Is it not? That is what the density, right? In particular volume, how much mass is there? Is it not? So when I say 1.17 gram per centimeter cube, 1.17 gram of HCl is present in 1 ml of HCl. That is what you understand. Okay, right? So now, what is molarity? For molarity, what is the thing? Number of moles of solute present in 1 liter of solution. That is nothing but 1000 ml of solution. That is what is the definition of molarity is, right? Number of moles of solute present in 1 liter of the solution, right? Fine. Now I have to make a page. Just a second. Right. So now we know that 1.17 grams of HCl is present. What is wrong? Okay, 1.17 gram of HCl is present in 1 ml of HCl, right? So can I calculate for 1000 ml of HCl, that is 1 liter of HCl, how much will be there? Can I say 1170 grams of HCl would be there? Is it not? Right? Now, what is molarity? Molarity is not the mass percent in 1000 ml. It is the number of moles percent in 1 ml. So I can directly write the number of moles of HCl in 1000 ml. That is nothing but the molarity. Right? That would be 1170 divided by the mass of HCl, molecular mass of HCl. That is 36.5. Hydrogen is 1, chlorine is 35.5. So this is the answer to this question. Okay, 1170 divided by 36.5 will be the answer to this question. I hope everybody is understanding. Right? Okay. Next. Is there anyone who didn't understand? Anybody want to repeat again?
Sir,
Yes. Tell me.
sir, in case it's not 1 liter and less than that, that's why we are multiplying by 1000. Sir.
Exactly. So
why
it's
are
like
we taking? So why are we assuming as 1 liter and multiplying by 1000?
Oh, because that is what is the definition of molarity. Molarity definition is that only you know the formula of molarity. Forget about the formulas. More than formula, the definitions of the concentration terms are more important. Right? So molarity definition says, now it is nothing but the number of moles. But what? Number of moles present in 1 liter of solution. Right? So that is what I need to calculate. In 1 liter of HCl, how much number of moles of HCl is there? That if you calculate, that is what is molarity then.
Yes, sir. Okay.
Okay, good. Next, moving on. Next, 5 ml of, what is this? I think it's NaOH. 5 ml of 1NOH. What is this?
Sir, N is normality.
Yeah, N is normality. What is HO is what I'm thinking. I think it's a printing mistake. Right? 5 ml of HO. Okay, fine. I think it's HCl. Right? We'll take it as 5 ml of HCl. Okay. The first one is HCl. First, 5 ml of HCl, 5 ml of 1N HCl, 20 ml of N by 2 H2SO4, and 30 ml of N by 3 H2HNO3 are mixed together, and the volume is made to 1 liter. Right? Find the normality of the resulting solution. Okay. Now again, guys, now that it's very simple. It's very similar to dilution only. It's just that we are mixing different aspects of different concentrations. Right? So what will be the molarity nu? Total number of moles of acid, that whatever the acids you have, total number of moles divided by total volume. Total volume, they're telling volume is made to 1 liter divided by 1. Right? So into 1000 we don't have to put because they are putting it in liters. If you put in liters, you don't have to put, you don't have to go for 1000. Right? So now all I have to calculate is total number of moles of the acid or total number of equivalents of the acid. Right? Now they're asking about normality. So it is N. Right? Normality is N. So instead of number of moles, it should be number of equivalents. And how do you calculate number of equivalents? Number of equivalents is equal to normality into the volume into 10 to the power minus 3. Why 10 to the power minus 3? Again, because it is in ml. Okay, normality. If it is going to be in terms of number of moles, it would be normality into volume. Sorry, molarity into volume into the power minus 3. Okay. Right. So now all I have to calculate is the total number of equivalents. So can I say total number of equivalents would be 5 into 1 into 10 to the power minus 3. Right. That is for HCl. Right. Because 5 ml, 1N HCl. Right. Plus 20 ml of N by 2 means what? 0.5 N. Right. 0.5 N into 10 to the power minus 3. This is for H2SO4 plus N by 3 HNO3. That is nothing but 1 by 3, which is how many ml? 30 ml. 30 ml of 1 by 3 into 10 to the power minus 3. Right? Now you add all these terms and multiply first all these terms and then add all these terms divided by 1. That is your normality. Okay? Easily you can do this. Right? Okay. Right.
Sir, the options are N by, so how do we calculate? Here we'll get only values.
No, nothing. So if I say N by 5, that is nothing but 1 by 5 N. If it is N by 10, that is 1 by 10 N.
Okay, sir.
Understood? Right? Like we went for the same thing. N by 2 means what? 1 by 2 N. N by 3 means 1 by 3 N. That's what we took in the calculation also here. Right? Okay. Next. Which of the following has the lowest value of Henry's constant? Right. Now Henry's constant, KH, is directly proportional to the molecular mass. This is what we need to understand. Okay. Henry's constant is directly proportional to the molecular mass, right? So obviously the lowest molecular mass, which one will have? Helium only will have. Okay. Right. Next. I hope everybody understood this. We're talking about Henry's law constant. I hope you remember what is Henry's law. P is equal to KH into X, right? As I increase the pressure, the solubility of a gas in a liquid will increase. That constant is what is called as your Henry's law constant, right? And that KH is directly proportional to the molecular mass. Yes, what happened?
Sir, X is mole fraction, right?
X is mole fraction, yes.
Sir, so mole fraction, number of moles of particular component by total number of moles of
Yes,
component.
yes.
So
Yes.
number of moles, if you consider like it is given mass by molar mass.
Okay.
So you are telling like KH is directly proportional to.
Oh, no. Why are you confusing with X and KH? X is a different term. KH is another different term. Are you able to understand?
Oh, okay, sir. Okay, we are rearranging this equation.
Yes. Don't worry about rearranging and stuff like that. This is what is the property of KH. Okay. KH increases with increase in molecular mass.
Okay, sir.
Okay. That's a constant, how it varies. Okay. Next. An aqueous solution of methanol in water has vapor pressure. Oh, now look at this. How do you answer these kind of questions? This question is from azeotrope, right? Whether it is going to be a minimum boiling azeotrope or a maximum boiling azeotrope, or this question even you can consider from the deviation from ideal behavior, positive deviation, negative deviation, right? Now, how do you understand this? Okay, right. Now say if water and water alone is there, that is only water is present, and say we have MEOH and MEOH only. Okay, right? H2 is there, MeO is there. Now these two are two different liquids. Okay, right. Now between H2O and H2O, I'm going to have some force of interaction, right? And what is the force of interaction called as?
Hydrogen.
Hydrogen bonding. Right. Between MEOH and another MEOH, I'm going to have same hydrogen bonding only. Right, guys, how do you decide whether I'm going to have hydrogen bonding or not? I think there are two criteria to look for. One is hydrogen donors. That is if I have a OH bond or a FH bond or a NH bond. And the second condition is that I need to have some lone pairs. Right? In both the cases, oxygen is having lone pair, and in both the cases, OH bond is present. So definitely in both the cases, hydrogen bonding is possible. Okay. Now, between H2O and H2O, what is the strength of hydrogen bond if you try to check? Right now, you see that each of the water molecule is going to contain two OH groups in two OH bonds, right? So here the hydrogen bonding is little stronger, right? Now, when I'm going to mix these two solutions, what is going to happen? I am going to have hydrogen bond between your what? H2O and NMA and then methanol, right? And this hydrogen bond, comparative to the hydrogen bonding in water, this is going to be weaker. Why? Because now I have 2H and 2H involved in the hydrogen bond, but here I have only 1H coming from this and 2H coming from this, right? So definitely understand that the the interaction when you make the liquid, when you make the solution, the hydrogen bonding between your H2O and MEOH is getting decreased, right? Now, if the intermolecular forces are getting decreased, what will happen to the vapor pressure? If I say the two
will increase, sir.
Yes, that's the logic, right? Now, what is vapor pressure, or how can I say this? More and more easily it will be able to go to the vapor phase. More and more vapor pressure will be there. Is it not? Right?
Yes,
So
yes.
now if the intermolecular interactions are very, very, very strong, that particular liquid will find it difficult to go to the vapor phase, and thus I'm going to have lesser vapor pressure. Right? So now can I say in hydrogen bonding, can I say in H2O, since hydrogen bonding is stronger, the vapor pressure is less because it is going to find it difficult to go to the vapor phase. Whereas in H2O and NMEOH, now do you see that the hydrogen bonding is weaker? So can I say here the vapor pressure is higher? Right? So what is the answer to this question? Definitely answer C. Right? The aqueous solution of methanol in water is going to have vapor pressure which is going to be more than that of water because the hydrogen bonding is getting weakened.
Sir,
Yes.
sir, could you repeat how methanol, like, why does the vapor pressure decrease?
The hydrogen bonding is becoming weaker.
Yes.
Okay.
Yes, sir.
If I have to show it, see, all the condition you have to understand is that I need to have hydrogen donors and hydrogen acceptors, right? Hydrogen donors are the one which are going to have the OH bond or FH bond or NH bond, right? And second condition is that the hydrogen acceptors should be having a lone pair. Okay, right. Now, in both the cases, the hydrogen acceptor capability is a little same only. Oxygen, I mean, in H2O, oxygen is having 2 lone pairs. In MeOH also, oxygen is having 2 lone pairs. That is not changing, right? But what about the hydrogen donor capacities? Now, here you see that here I have this OH bond, this hydrogen can be donated, or this OH bond, this hydrogen can be donated. If it is going to be with water, right? So totally, if you check, I can have 4 OH bonds present in water and all of them will be able to involve in hydrogen bonding, right? But when you go to H2O and MeOH, as I said, the number of lone pairs is not changing, 2 and 2 only. But look at the number of hydrogen donors. Here 2H will come, but here there is only 1 OH. So here I have only 1 hydrogen, right? So the number of hydrogen donors are getting decreased from 4 to 3.
Yes, sir. Got it.
Right? So obviously, you understand that the hydrogen bonding is weaker here. Okay? Right. Next question. Right. Next question. 12 grams of urea, right? 12 grams of urea is dissolved in 1 liter of water. Okay. 684 grams of sucrose dissolved in 1 liter of water. Okay. The relative lowering pressure of urea is water. Right. Now, how do you calculate the relative lowering of air pressure? Del P. What happened? Why is it going away? That's the problem. Okay. I hope this time it works. Okay, right. So now they're telling we have to compare your relative lowering of air pressure between your urea solution and your glucose solution. Okay. So now how do you calculate relative lowering of air pressure? Del P divided by PA naught or PV naught is equal to XB, right? Where A is the solvent, right? And B is the solute. Is it not? Let us do this. So now del P by PA naught for urea solution, let us calculate first, right? Urea solution we calculate. Now you see that it is, we have to calculate XP, that is nothing but the mole fraction of urea, right? This A is water. Okay, right. So now 12 divided by, what is the formula for urea? NH2, C double bond O, NH2. Right? NH2, C double bond O, NH2 is what is the formula. And if you calculate the molecular mass will be 60. Right? Divided by 12 by 60 plus 1 liter of water. Okay. Now 1 liter of water, we have to remember what is the number of moles of water. Right? Now all that you have to understand is density of water is 1 gram per ml. This is your density of water. Okay, so I can tell that 1 liter of water is going to contain 1000 grams of water. Is it not? The same goes with your HCl solution also, if you remember. If I say 1 gram per ml means 1 gram of water present in 1 ml of water. So in 1 liter of water, that is 1000 ml, I'll have 1000 grams, right? So what you understand is, now this is the number, this is the mass of water present in 1 liter of water. So what will be the number of moles of water? Number of moles of water would be 1000 divided by 18. That's what will come here. 1000 divided by 18 would come here, right? This is the value you will find for vapor pressure of, relative lowering of vapor pressure of urea solution, right? 12 by 60 divided by 12 by 60 plus 100 by 80, 1000 by 80. Okay, next. I have to make a page. 1 second. Right. So now let us calculate the del P divided by PA naught of your sucrose solution. Right. Now sucrose formula is what? C12H22O11 is what is your formula for glucose, sucrose. Right. So if you calculate your molecular mass of this, I think it will be how much? 72 plus 22. 72 plus 22 is 94. 94 plus 16 into 11. Can you calculate this? 12, that is 70, 84. No, sorry, 94 plus 16 into 11. Sorry, 16 into 11. Yes. So 66. One time, then 7, 176 plus.
Sir, how 94, sir? 12
Sir,
into 12.
12 into 12, 144.
Oh, yeah. 12 and 12 will become 144. 144 plus 22. 144 plus 22 will become 166.
66.
166, right? So 166 plus to 176. This is 11 times 66. This is 17. Yeah, that's correct. Right. So 144. Yeah, 166 will become 342. Right. Okay. This is the one. This is the molecular mass of C2H sucrose. Now, how will you write? What is the given mass? 684 grams of sucrose. 684 grams of sucrose divided by the molecular mass divided by 684 divided by 342 plus again water 1000 by 80. Right now, can you see that this value 684 by this thing is nothing but 2? So 2 divided by 2 divided 2 plus 1000 by 18. Right. Whereas for the previous one, 12 divided by 60 is 1 by 5. Right. 1 by 5 is nothing but 0.2. Right. Again, this value will be 0.2. Right. So you understand that it is actually going to be, if I just write it, if I just make one more page. Right. So we have what is that? Del P divided by PA naught of urea is 0.5 divided by 56. Why am I saying 56? Because 1000 by 18, the value is 55.5. If you calculate it. Okay, so 0.5 by 56, whereas your del P divided by PA naught of sucrose would be 2 divided by 57.5. Okay, right. So now which is going to be higher, which is going to be lesser? You have to calculate it, right? So definitely, I think this value is greater. Is it not? Sucrose's value is greater even if you don't calculate it, right? All I can understand is that this sucrose value is greater for sure. Is it not? So if sucrose this thing is greater, so what should be the answer then? So it is double that of sucrose solution. Then this is there, right? The relative of urea solution is going to be lesser than that of your sucrose solution, because we concluded that definitely sucrose solution is going to have a greater relative vapor pressure, right? So what should be the answer to this question? B should be the answer. It is going to be less than that of sucrose solution. Yes. Anybody has any questions? Okay. Fine. Moving on. Right. Next, formation of solution from two components can be considered as One, pure solvent separated, pure solvent to the separated solvent molecules delta H1, pure solvent to separate solute molecules is delta H2, and separated solvent to the solute molecules will give me delta H3. Okay. Okay. Right. Now, what you understand is when you want to make a solution, right? Say this is your solute. Okay, this is your solute, and this B is your solvent. Right? And obviously in your solution, we are going to have AB interactions. Okay. So how you should form this? Now you understand that this A and A bond has to be broken. That is the interaction between solute and solute has to be broken. The interaction between your solvent has to be broken. And this interaction has to be made. Is it not? So you have to break your solute-solute interaction. You have to break your solvent-solvent interactions. And you have to make your solute-solvent interaction. Right? And always remember, whenever bond is broken, right, that means energy has to be supplied. Right? And whenever bond is made, energy is released. Okay, whenever bond has to be broken, obviously that's understood, right? Whenever you want to break a bond, you have to supply energy. And whenever a bond is formed, it is going to give us energy because it is going to get stabilized. Right? And another thing, what is the sign convention we follow? Right? The sign convention we follow is this, I'll tell you. Right? The sign convention we follow is energy absorbed should be a positive value and energy released should be a negative value. If I say, for example, in a process, during a process, 5 joules of energy is absorbed, right? Then I will give the energy value as +5. Same way, if I tell that in a process, 5 joules of energy is released, right? Then I will give that value as -5. The E value is -5, not +5, right? So energy released is negative, energy absorbed is positive. Right. So now, can I say that the pure solvent getting separated, that is nothing but the breaking a solute interaction, delta H1 is there. So can I say this is minus delta H1? I have to consider this as, right? Same way, pure solute to separate solute molecules, can I say this is going to be minus delta H2? Right. And whereas when you're going to form the interaction, that is between a solute and solvent, this is going to be a positive value. Right. So how you should write this? Overall, you should understand that delta H3 alone should be positive, that is this, and delta H1 and delta H2 should be negative because these are energy. Oh, we are getting exactly opposite. This should be positive because these are energy absorbed, whereas this value is going to be negative. Is it not? Because energy is absorbed. Means
the option B.
Yeah, option B should be the answer. Absolutely. Right. Delta H1 positive, delta H2 positive, but delta H3 is going to be a negative value because it is going to get released. Okay, right. Moving on. Next, the system that forms maximum boiling azeotrope. Right, these are all you have to remember. Okay, right. But still, even if you don't remember, actually, you'll be able to understand certain things. When you want to form maximum boiling azeotrope, right? A maximum boiling azeotrope is actually going to show negative deviation from Raoult's law. Negative deviation from Raoult's law, right? What do you mean by negative deviation? The vapor pressure expected, or sorry, vapor pressure observed, right, is going to be, or we can write it, vapor pressure observed is going to be lesser than the vapor pressure theoretically calculated. Is it not? That is what is negative deviation. Obviously, if both the observed pressure and the theoretical pressure, calculated pressure is going to be same, then there is no deviation. That is ideal solution, right? If this observed pressure is greater than what we expect, that will be the positive deviation. And obviously, if the observed vapor pressure is lesser than the theoretical pressure, then that is definitely going to be your negative deviation. Right. Now, for it to show negative deviation, that is, the observed vapor pressure is going to be less. Why it will be less? Can I say the intermolecular forces are very strong? Can I say that? Exactly. We have seen that similar kind of question previously also. What happened to HCl and H2O and MeOH? Right? The vapor pressure was decreasing because of what? Because the vapor pressure was increasing because of what? The hydrogen bonding is becoming weakened. Right? So now for exactly opposite now. Now the vapor pressure is decreasing. Why? Because I'm going to have very strong interactions in the solution. Okay, right? Fine. Now let us try to understand this. Right. Now let us take the first option, carbon disulfide with acetone. Right. Now carbon disulfide is CH2. Acetone would have had CH3, C double bond O, CH3. Right. Now, if acetone alone would have been present, right? If acetone alone would have been present, you would have had what kind of interaction? There is no hydrogen bonding possible here because there is no OH bond, there is no FH bond, there is no NH bond, nothing is there. Right. So the only thing which is possible is your dipole-dipole interaction. So now do I show this? These two are two methyl groups, and I will show another carbon atom having two methyl groups. Now we know that this bond is going to be highly polar. So this is going to have a del plus, this is going to have a del minus, this is going to have a del plus, this is going to have a del minus. Right. Now you see the del minus of one oxygen and the del plus of the next carbon molecule, that is going to have some interaction. Right. Now this is what is called as your dipole-dipole interaction. Okay. Now this dipole-dipole interaction is going to be quite strong, right? Because it is going to be between carbon oxygen, right? Now in CS2, right? In CS2, there is, even though there is going to be an electronegative difference between carbon and sulfur, but it is not going to be as strong as this. Is it not? It is not going to be as strong as in the case of acetone, right? Now what is going to happen is, I am going to have some, now when I'm going to make the solution, I am going to have some kind of interaction between your CS2 and your acetone, right? So now what is happening overall? CS2, there is not much changes, right? Nothing much changes in CS2. But now what happens to acetone? Acetone was having interaction with acetone itself in the form of dipole-dipole interaction. But now this interaction is going to be a weaker interaction. Is it not? This interaction is going to be a weaker interaction. So if the interaction is weaker, I obviously say that the vapor pressure will increase, not decrease. So this will show what? This will show positive deviation from this thing, or it is going to be a minimum boiling azeotrope. Right? Like this, we need to check. Right? Let us check for option B. What is happening? Benzene and toluene. Okay.
Sir?
Yes, tell me.
Sir, can you say like the solute-solute interaction and solvent-solvent interaction is higher than solute-solvent?
Yes, obviously. Solute-solute interaction and solvent-solvent interactions are greater than solute-solvent interactions. Definitely, it is going to show negative deviation. Yes, absolutely.
Okay.
Correct. Negative deviation, positive deviation. Right?
Yes.
Because the interactions are weaker, more vapor pressure in the solution.
Yes,
right? Okay. Now, forget about toluene benzene. It is not going to be much different, right? Toluene benzene is actually an example for an ideal solution. Okay. Now, let us consider acetone and chloroform. Right. Now, what you see is that acetone is going to be similar. Right. Acetone, nothing changes. But what is coming is chloroform, CHCl3. Right. Now, please understand that CHCl3 can also have dipole-dipole interactions. Is it not? Because that is also having a CCl bond, which is highly polar. That is also going to have del plus, del minus, stuff like that. Right? Fine. Now, CHCl3 is going to have dipole-dipole interaction with CHCl3. Right? Now, when I'm going to mix these two, right, I am going to have CHCl3 having interaction with, acetone having interaction with your CHCl3. And that dipole-dipole interaction is going to be very strong. Right? That interaction between this and this, whatever the interaction you're going to have, that is also going to be dipole-dipole interaction only, right? But since both of them are going to show that, so this dipole moment, they mix together, there will be a very strong interaction between acetone and chloroform. Okay, so now this shows that in the solution, I'm going to have a very strong intermolecular force, and that is going to make sure that it is not able to go to the vapor phase, and so the vapor pressure is lesser than what we expect. Right? So can we conclude this as the option now? See? Okay. Right? Like this only you have to approach, or else you have to cram up. Okay. Whatever the list which is given in your NCRT under negative deviation, positive deviation, minimum boiling azeotrope, positive maximum boiling azeotropes, all those things you have to mug up. If not, you have to attempt it like this. This is the overall thing. Right? This is how you work out. Okay. Right? Any questions anybody has? Okay, fine. Moving on. Right. Next, the molal freezing point of water is this much. Right. The molal freezing point of water is 1.86 degrees Celsius per mole. When I say per molal means per mole or per small m molality. Okay, fine. Therefore, the freezing point of 0.1 m NaCl in the solution in water is expected to be. That's very simple, right? Now, for 1 m solution, we are having 1.86, right? So now, what is this thing here? There is 0.1 m. Right, so definitely that is going to be x. If I want to calculate this, right, what will you do? This is divided by 10. This also will be divided by 10. So it should be what? It should be minus 0. Sorry.
Sir, 1.86 is Kf. The constant is given.
1.86 is
Constant of molar freezing point.
Freezing point. 1.8 is the freezing point. Right. So now, if it is for 1 m, it is 1.86. For 0.1 m, it should be what? 0.186. Is it not? Right. So where is 0.0186? Obviously here.
Sir, is the freezing point and freezing point constant or same?
What kind of?
Freezing point and the freezing point.
Oh, it's freezing point constant. Oh, I am so sorry. So that's absolutely true. We are right. We are reading the question in an entire wrong sense till now. Right. We'll do it again. Right. So what you understand is the molal freezing constant. That is nothing but your Kf value. Right. The Kf value of water is 1.86. That's what they're telling. Okay. Therefore, the freezing point of 0.1 m solution, NaCl solution in water is expected to be. Right. Actually, this should not be big M. This should be small m. Because we know the formula, right? Delta Tf is equal to Kf into m. That is molality. Right. Now, delta TF is what we need to find. Delta TF is equal to 1.86 into the molality, that is 0.1. So delta TF will be equal to 0.186. This is not the freezing point. This is the depression in freezing point. How will you calculate the freezing point of the solution? Now, depression freezing point, how do you represent? It is the freezing point of water minus the freezing point of solution. Is it not? That is how you represent, right? Delta TF, how do you represent? That is change in the freezing point, right? Freezing point of water minus the freezing point of solution, right? I know freezing point of water is 0 degrees Celsius. Now, if you are closely watching this, we generally go for substituting the values in Kelvin, right? But here we're directly substituting the values in degrees Celsius. Why? Why? Because the Kf value is given in degrees Celsius. If it was given in Kelvin, then definitely we must use a temperature in Kelvin only, right? But since now it is going to be given in terms of degrees Celsius, we will calculate the temperature also in degrees Celsius only. Okay, so it's like 0 minus the freezing point of solution is 0.186. So obviously TF of solution is minus 0.186 degrees Celsius. Answer is correct, but what we did was wrong. Okay, still the option is option B only. Is everybody able to understand what we did here? Simple formula. Simple, what is the formula I have to substitute? Delta TF is equal to Kf into M.
Yes, sir.
Right? Okay. Next, moving on. What is the osmotic pressure of 0.002 m molar decimeter cube sucrose solution at 20 degrees Celsius? Take the molar gas constant as 8.314. That's it. Now, direct substitution formula, pi. Osmotic pressure is equal to C into R into T, where C is the molarity. Right? C is the molarity. And molarity is given or not? Mole per decimeter cube. What is 1 decimeter cube? 1 decimeter cube is 1 liter. Okay, 1 decimeter cube is 1 liter. 1 centimeter cube is 1 ml. Okay, right. So now directly I can take it as mole per liter. That is nothing but the molarity. Right? I can substitute the values now. 0.002, that is the molarity, into the R value is 8.314. We have to take it. That is what is given. And temperature is 20 degrees Celsius. Now, in this case, you cannot use degrees Celsius. You have to go for Kelvin, because you can see here, it is joule per kilo, Kelvin per mole in our value, right? So here you'll use 298 Kelvin, and you can calculate and get the final answer.
So 293, right?
Ah, sorry, 293. Yes, absolutely. Okay, done. Moving on. Okay, next. Camphor is often used in molecular mass determination because it is readily available. It has very high cryoscopic constant. It is volatile. It is a solvent for organic substances. It is definitely not, right? It is readily available. No, right? We know camphor, right? If you keep camphor in what is that? In air, say if you keep it outside, what is going to happen? After some time, you will see that it has actually gotten smaller.
Sublimation.
Exactly. Sublimation happens, right? Sublimation, why it happens? Because it is going to be highly volatile. What is volatile? Volatile means easily escaping into the gaseous state. Okay. So the answer to this question should be it is because it is used because it is going to be highly volatile. Okay. Right. Next. A 5% solution of cane sugar of molecular mass. Yes, Kana.
Sir, what is cryoscopic constant?
Oh, cryoscopic constant, that Kf value is there, right? That is what is called as.
Okay, sir.
And your what is Kb called as?
Ebullioscopic.
Ebullioscopic constant. Right. Okay. Anyways, fine. Next question. 5% solution of cane sugar. What is cane sugar? Sucrose. Okay. Cane sugar is sucrose. Fine. They are going to use the molar mass also. Calculate 342. Remember that. Okay. So a 5% solution of cane sugar is isotonic with 1% solution of an unknown solute. What is the molar mass of the unknown solute? Guys, whenever we say two solutions are isotonic, that means they are going to have same osmotic pressure. This is the thing you will remember. Right? Isotonic solutions will have same osmotic pressure. Right? So what you understand is the pi of the cane sugar solution is equal to the pi of the unknown solution X. We don't know what is X. Okay. We have to calculate the molecular mass of X also. Right. Let us substitute the formulas now. Right. So you have 5% solution they are given. Right. Now 5% solution means, see, now in the C, basically pi is equal to C into R into T. Right. Where C is the molarity. I know that. Molarity is equal to number of moles by volume. Right. So somehow we need volume and number of moles. Okay. And you have to calculate it from this 5% solution. Okay. Now what you understand from this 5% is that now again percentage can be of three types. It can be W by W, it can be W by V, or it can be V by V. Is it not? W by W or W by V or V by V. Right. Now in this case, only if you take the percentage as the W by V, then only you'll be able to answer the question because we have volume term in the molarity. Okay, we have volume term in the molarity. So definitely you have to use this percentage value as W by V, then only you'll get the answer. If you use W by W or V by V, it doesn't make sense. Right? These and all are small things you have to remember or you have to look for. Okay. Fine. Now, what do you mean by 5% solution? 5 grams of cane sugar is present in 100 ml of the solution. That is what you understand. What is WAV percentage? What is the definition of that? It is the weight of the solute present in 100 ml of the solution. That is what is the definition for W by V. W by W is, it is the weight of solution present in 100 grams of the solution. Same way for volume by volume, it is volume of solute present in 100 ml of the solution. Okay. So when I say 5% W by V percentage, that means 5 grams of cane sugar is present in 100 ml of the solution. Okay. Right. Same way. Now let us substitute the values here. Let us maybe make a slide. Right. So now I write pi of what is that? Sucrose, that is nothing but cane sugar, is equal to pi of X. Let us substitute the values now. Pi is equal to C into R into T, where C is the concentration of sucrose, Temperature is same because they have told. Right? Temperature. Yeah, they are not given anything about the temperature, so we'll take the temperature to be constant. Okay. So this is sucrose, same, that is equal to C of the X into R into the same temperature. Now directly what I can do is I can cancel these RTs. Right? I can directly cancel these RTs. Right? So only thing which is remaining is concentration of sucrose is equal to the concentration of X. All right, let us calculate the concentration of sucrose now. We already know that 5 gram of sucrose, that is cane sugar, in 100 ml solution. Right? So I will write that now what I have to calculate is number of moles by volume. Right? So molarity of sucrose will be equal to number of moles that is given mass by molecular mass. What is the given mass? 5 grams. 5 grams of cane sugar is present. Right? So 5 divided by 342, that is the molecular mass of sucrose, divided by the volume. Volume is 100 ml into 1000 in the numerator. Right? Same way, this should be equal to the molarity of X. And how do you do that? 1 gram is there. They're given you what? 1% solution, right? 1% solution. That means 1 gram of that X is present in 100 ml of solution. Right? So 1 gram is the given mass divided by the molecular mass of X. I don't know. Right? That is what we need to calculate, right? Molecular mass of X is what we need to calculate, divided by again 100 ml into 1000. I put 1000 here. This should be here. This should be 1000, right? So this 1000 and this 1000 gets cancelled. This 100 and this 100 gets cancelled. So what is remaining now? 5 divided by 342 is equal to 1 divided by the molecular mass of X is what is remaining. So what is molecular mass of X? That will be equal to 342 divided by 5. That's the answer. So approximately it should be around 60.
68.5.
68.5. That's it. Okay, this is how you calculate the question. This is how you calculate. So first thing to understand is what is hydrotonic, same osmotic pressure. Second thing is in this day, whenever molarity is used and then they are giving you some percentage, not an
Your voice is breaking.
Now is it right?
No, sir. Still breaking.
Still breaking. Oh, I don't know what the issue. Let me join again. But okay.
Yes, sir.
Now is it fine?
No, sir.
No, sir. Now it's not.
No, sir.
fine.
No, sir. No, sir.
Okay. So what I do is, if I will, someone else will be made host. Okay. So when I come back, I make me host again. Then only I can get this.
Sir, or you make somebody host them. Sir.
And then go. Okay. Got it. Who will take responsibility? You want to take?
Yes, sir. I'll do.
Okay. I'll make you the host and then we'll change into. Okay, I will leave and will come back.
Okay. Sir.
Yeah, guys. Now is it fine? The voice?
Yes, sir.
Yes, sir. Now it's fine. Sir.
Okay, fine. And now can I make the host? Oh, make me host, Karna. You want?
Yes, sir. One second.
Yeah. Okay, I'm the host.
Sir, I made you.
Yeah, got it. Yes, thank you. Right. So we were seeing this question and we understood that isotonic solutions are going to have same osmotic pressure. Right? Okay. Moving on, let me hide this. Let me hide this. And I'll go to the next one. Okay, next one. Next, osmotic pressure of what? What is M? Why is there a lot of printing mistake? Okay, I think what M is it? I don't know. I think it's 1M.
Sir, I think it's 1
1
m.
molar.
1M. How do we do, right? If they just say M like that, we do, it's 1M. Okay. So osmotic pressure of 1M aqueous solution of NaCl is dash osmotic pressure. Oh, is equal to, or whatever it is dash to the osmotic pressure of 0.1 solution of glucose. Now, guys, this is where your Van 't Hoff factor comes into the picture. Now, tell me, in which kind of solutions you will use Van 't Hoff factor, in which case you will not use Van 't Hoff factor? Tell me.
Sir, where ions are formed, we have to use Van 't Hoff factor. Where
Okay.
ions are not formed, suppose in
Only in the
like-
case where ions are formed, you'll use Van 't Hoff factor. Any other case you'll use?
Sir, when association or dissociation takes place.
Absolutely, absolutely. Right. So when association, that is, when two molecules combine together to make a dimer, for example, in the case of your B2H6, how do you form B2H6? BH3 plus BH3, right? Dimer, right? So that is called as association, right? And whenever you have an ionic solution like NaCl, for example, right? Now, in that case, you will be using dissociation. And in both the cases, you will be using your Van 't Hoff factor I. And when either of these are going to happen, say, for example, in glucose, nothing will happen. Neither association nor dissociation. It is not going to form any ions. It is not going to form any dimer, right? So in those cases, you will not use your Van 't Hoff factor. Okay. Now, Van 't Hoff factor, how do you define it, people? Van 't Hoff factor is equal to, please don't give me any formulas. Okay. If you go by the formulas, how many formulas you'll remember, right? It is always good to go by logic, right? Now, how do I define my Van 't Hoff factor is nothing but it is the total number of moles at equilibrium. Okay. For what I'm trying to say, for example, if you have NaCl, you would have had Na plus and Cl minus getting formed, right? So if I start with some 1 mole, initially would have been 0. Say, assume that it has not started yet, right? Now, when I'm going to reach the end, that is at the equilibrium, now I don't know, some alpha would have gone as out of the 1 mole, some alpha moles would have actually undergone the association, right? And obviously, if alpha moles are going to react here, alpha moles will come here, alpha moles will come here, because 1:1, all the ratios are 1:1:1. I hope you get this, right? So can I say the total number of moles in this case is equal to 1 minus alpha plus alpha plus alpha, right? So can I say it is equal to 1 plus alpha, and that will be equal to the Van 't Hoff factor I. This is always true. Okay, total number of moles at equilibrium will be equal to your Van 't Hoff factor I. And what is this alpha called as?
Degree of dissociation.
Yes, it's called degree of dissociation. Or if it is going to be in terms of association, it is going to be called as degree of association. Right? Okay. Now, if they don't give you anything about this alpha value, that is out of 1 mole, how much is undergoing dissociation? That is what is degree of dissociation, right? Now, if they don't give you anything, assume that alpha value is 1. That means out of 1 mole, all the 1 mole is actually undergoing dissociation. Okay, but if they give you some alpha value, you have to take it. If they tell that 80% dissociated, then what will be the alpha value? When I say
0.8.
right? So the percentage divided by 100 is what is going to give you your alpha, because you understand for alpha, the scale is between 0 to 1. Whereas for percentage, the scale is between 0 to 100, but everything means the same. Out of 1 mole, how much undergoing dissociation is alpha? Out of 100, how much undergoing dissociation is percentage dissociation? Is it not? So when I say when the percentage dissociation is 80%, then obviously alpha value is 0.8. When I say alpha value is 0.3, then the percentage dissociation is 30%. Okay, right. So now we understand that nothing is given in this question. So definitely we can see that what is that? Alpha value is 1. So we can assume that the I value is what? 2, because 1 plus 1 will become 2. Okay. Now keeping this in mind, I'll just make a page. Right. So now, okay, what was the question? the osmotic pressure of 1m aqueous solution. Okay, so now pi of NaCl will be equal to I into C into R into T. Why am I taking? Because NaCl undergo dissociation. And I value will keep it as 2 into C value is 1m, that is 1m concentration, R into T. We'll just keep it as R into T. Right. Same way, pi of glucose solution. Now there is no I here, but what is the concentration? Concentration is 0.1. 0.1 into R into T. And temperature is changing or temperature is same? Okay, nothing given about the temperature, so temperature is same. Right. Now what is happening? This is 2 times RT, right? Whereas this one is 0.1 times RT. Is it not? Right. So obviously it should be what? The osmotic pressure of NaCl is 20 times the osmotic pressure of glucose. Is it not? If you multiply this by 20, then you'll get this, right? Is it not? So pi of NaCl is 20 times the osmotic pressure of glucose, right? But I think it's a printing mistake, right? So because I think this is 0.1. Okay, only if it is 0.1m, then I can say that it is going to be nearly double the value. If I put 1m, obviously what are you seeing? If I put 1 here, you're getting 2 RT. I hope you're getting what I'm saying, right? Here we have kept the pi of, what is it? Oh, we're going to the previous question, sorry. Right, pi of, we are taking the concentration of C, this thing, NaCl as 1. That's why we're getting 2 RT. But if I take it as 0.1 m, what is going to happen? Now this is going to become 0.2 into R into T. And what is the value here for this? 0.1 into R into T. So obviously if I multiply this by 2, you'll be getting this. Is it not? So obviously you can understand that your pi of the NaCl is twice the value of pi of what is that? Glucose. So obviously it is nearly double. Okay, just give me a moment, I'll be back. Okay, I hope everybody got this question. So answer will be nearly double. Okay, right. Moving on. Next. 4 solutions of K2SO4 with the concentration of 0.1 m, 0.01 m, 0.000, I mean 001 m and 0001 m are available, right? The maximum, what is that? Value of Van 't Hoff factor I will correspond to what? Doesn't change, right? C doesn't change with concentration. When alpha doesn't change with concentration, whereas your Van 't Hoff factor I will change with concentration. Okay, right. Now we have decided that the total number of moles at equilibrium is what is I, right? Okay. Now if you go for K2SO4, right? That will give me 2K plus SO4 2 minus. Okay, right. Now, for example, say let me take 0.1 m. That means 0.1 moles of K2SO4 are there, and 0 and 0. Okay, right. Now assume that entire K2SO4 is undergoing dissociation. We don't know. I will assume that alpha is 1. Right. So can I say 0.1 minus 0.1? Right, entire 0 of this thing is becoming this thing. So this will become 0. So here will get 0.1 and 0.1. Right. So now what will be the I value here? Can I say 0.2? Okay. Right. But again, if it is going to be for 0.01 m, you'll get 0.002. If it is 0.001 m, then you'll get 0.002. If it was 0001, then you'll get 0002. Oh, sorry. I am so sorry. This is wrong, right? If it is 0.1 of this reacting, how much should come here? 0.2 should come here, right? Because the ratio is 1:2:1, right? So if 0.1 of this will react, 0.2 you'll get here, 0.1 will get here. So I value here is 0.3, not 0.2. right? So obviously, which is going to have the highest Vanta factor, which was going to have the highest concentration, right? So obviously, that is going to be 0.1 m solution. That's the answer, right? Okay, moving on. Okay, when and why molality is preferred over molarity in handling solutions in chemistry, right? When temperature is changing, obviously, right? When temperature is changing, your molarity value will change and your molarity value won't change. That's the answer also. When temperature is changing, why are you using? Because molarity will change with temperature, whereas molality won't change with temperature. That's very simple. Okay, that we've already seen. Next, which solution has a higher concentration? Which solution has higher concentration? 1 molar or 1 molal of the same solute? 1 molarity being 1 and molality being 1, which is going to have a higher concentration of the same solute? But it doesn't make sense. Both of them should have the same concentration only. Okay. Mass of solvent. Here it is volume of solution. Volume of solution, we will take the volume of solute and the volume of solution. Here we are taking only the mass of solvent only. Okay. So comparing this value and this value will be higher. That means the molarity value is lesser. Okay, I hope you're getting this, what I'm saying, right? This is volume of solution, right? Volume of solution is volume of solute plus volume of solvent. Both the volumes you have to add, but in this case, we'll be using just the mass of solvent. Okay, right. So obviously, this term is definitely going to be huge compared to this mass of solvent because we're using two terms here, volume of solute and volume of solvent. Right. So if this term is higher, then definitely the molarity is lesser. And if this term is lesser, this value is higher. So we can always conclude that the molarity is going to be greater than the molarity. And you can see this, whatever explanation I've given you, you'll be able to use this. Okay.
Sir.
Yes.
So, but they've given one, right? 1 molar and 1 molar.
1. So that means obviously we're talking about the concentration. Concentration about the number of moles of solute. Okay, number of moles of solute here.
Sir, so we have to assume that N is 1.
Yeah, you have to assume that here M is 1 and your this M is also 1. If that's the case, if this volume is higher and if I multiply this with 1, obviously what you understand is the number of moles of solute here will be higher because this value is 1. So 1 into volume of solution is equal to the number of moles of solute. And in this case, 1 into mass of solvent is equal to the number of moles of solute. Right? So which value will be greater? The volume of solution is greater. So obviously number of moles of solute in this will be higher. Right? So molarity is going to have higher concentration. When I say concentration, I'm talking about the number of moles of solute. Okay, but this question is so stupid. Okay, that does not make much sense. Okay, but still, just for the sake of answer, we can tell that the number of moles of solute in molarity will be greater than the number of moles of solute in molality, right? But it doesn't really make sense. Okay, anyways, moving on. Don't worry about this question. Okay, next. Right. V1 cc of a solution having molarity M1 is diluted to have molarity M2. Right. Derive an expression in terms of M1, M2, and V for the volume of volume of water required to be added. What are they telling is initially, right? We had V1, so V1 volume, that is V1 volume, and M1 was the molarity. Right? Now, what are we doing? Now we are doing V1 plus some more amount of water we are adding. Is it not? Right? V1 is already there. We are adding extra amount of water to dilute it. And in that process, this M1 becomes M2. Is it not? Right? Now we know how dilution works. The number of moles of solute is not going to change, only the volume will change. Right? So can I say initially the number of moles of solute would be V1 into M1 into 10 to the power minus 3. Okay. Now, when I go to the new molarity new, this is the number of moles of substitute, that is M1 V1 into 10 to the power minus 3 divided by total volume. Now, total volume is what? V1 plus X. Right? And this molarity new is nothing but your M2. Is it not? Right? So now we can, now only unknown is what here? X. This X is what? X is the volume of water required to be added. Amount of water you added are on top of V1. That becomes V2. Right? So you can easily write an expression now. Into 10 to the power 3 will come. Right? 10 to the power 3 and 10 to the power minus 3 will get cancelled. So all that we have is M2 is equal to M1 V1 divided by V1 plus X. Right? So let us multiply this side. M2 into V1 plus X into M2 is equal to M1 V1. Right? Now let us keep X M2 on this side. You will get M1 V1 minus M2 V1. So X value would be M1 V1 minus M2 V2 divided by M2. This is the equation. Okay, X is equal to M1 V1 minus M2 V2 divided by M2. Hello, everybody is getting this. Very simple. Right? Anybody wants me to explain again what happened here?
No, sir.
Right? Moving on. How much is the molality of a solution different from its molarity? Okay. How is the molality of the solution different from its molarity? That you can write in terms of your definition also. Molality is the number of moles present in 1 kg of solvent, whereas molarity is number of moles of solute dissolved in 1 liter of the solution. Right? You write the definition and you get the marks. And you write the 2 formulas also and you get the marks. Okay. And you can also write it is temperature dependent, it is not temperature dependent. Molarity is temperature dependent. Molality is temperature independent. That also you can write here. Okay. So three points you can write. One is the definition, one is the formula, and third is the temperature dependence. Okay. Right. Maybe I'll write the points. One is the definition, right? The formula and your temperature dependence. Okay, 3 things you have to write. Right. Next. Why the solubility of Glauber salt first increases up to 34 degrees Celsius and then decreases? Why the solubility of Glauber salt first increases up to 32.4 degrees Celsius, and if I still increase the temperature, it is decreasing. Increase in temperature, increase in solubility. That's what we expect. But after a point of time, what happens? I will have Na2SO4 anhydrous. Let me check this question. Okay, tomorrow I'll tell you the answers. Okay, I don't want to, give my own whatever it is. Right? Let me check and come back to you. Right? Instead of telling something wrong, it's always good to check. Okay, you also check. Okay, I'll also check. Remind me about this question tomorrow. Okay, right. We'll go to the next question. Right. How are substitutional solids obtained? I think this is not from this chapter. This is from solid state. Don't worry about it. Okay, next. How solubility of gas and water relate to their Henry's law constant the same temperature and pressure? Right now they're asking, we know the formula, P is equal to KH into X. Okay. Now they're asking how the solubility of gas and water related with their Henry's law constant. Right? How is it that the Henry's law constant and KH are related is what they're asking. Right? Now, if I assume that the pressure is constant, right? If I assume the pressure is constant, you can write X is equal to KH divided by, X is equal to P divided by KH, right? So now obviously what you see is that the X and the KH are inversely proportional, right? X and KH are inversely proportional, right? From this equation, X is equal to P by KH, right? And another thing what you understand is X is nothing but your solubility, right? And we know if I increase the temperature, the solubility what? No, understand this. For the gas in water, right? If I increase the temperature, what do you think will happen to the solubility? I'm talking
they
about
escape
the
out.
Decrease, sir.
exactly, they escape out, right? The gases will try to escape out, so their solubility decreases. So what I can say is that the X value and your temperature are inversely proportional, because if when I increase the temperature, the gases are escaping and they are not getting soluble, right? So if X is inversely proportional to T and if X is inversely proportional to KH, can I tell that the KH is directly proportional to T?
Yes, sir.
Right? So these are the things you will understand. Okay, right. Moving on. Okay. 2 grams each of solutes A and B of molecular mass of A greater than the molecular mass of B result in dissolved separately in 20 grams of solvent C, which will show a greater lowering of vapor pressure and why. Right, guys. Not only this, I am going to give you one thing very, very important. Right, the colligative property, any colligative property, if you check, right, it is actually inversely proportional to the molecular mass of the solute. It is always going to be true, right? This is always true, right? So if A is having higher molecular mass, that means it is going to have a lower colligative property, and B is having lower molecular mass, and that is going to have a higher colligative property, right? So which will show a greater lowering of vapor pressure? B is the answer. And why? Because any colligative property is inversely proportional to the molecular mass. I can prove it to you if you want. For example, say you take I don't know, anyone you can take, say delta TF is equal to KF into M, right? Now how will you write M? M is number of moles of solute divided by mass of solvent, right? How do you write the number of moles of solute? Given mass divided by the molecular mass of solute. Now you see that delta TF is actually inversely proportional to the molecular mass of solute. Not only this, any colligative property matter is going to be inversely proportional to the molecular mass of the solute. Okay, right? Fine. Moving on. What will happen to the boiling point of a solution if the weight of the solute dissolved is doubled, but the weight of the solvent taken is halved? That's a good question. Now look at the question again. What will happen to the boiling point of the solution? That is, delta TB is what we're talking about. Delta TB is delta TB of solution minus, sorry, the TB of solution minus the TB of water is equal to KF into M. And we can write this again. Delta TB of solution minus, TB of solution minus TB of H2O is equal to KF into number of moles of solute divided by the mass of solvent. This is what we do. Okay. Now, what I'm telling, if the weight of the solute dissolved is doubled. Now, if the weight of solute dissolved is doubled, can I say the number of moles will also be doubled? Because number of moles is equal to given mass or molecular mass. If the given mass is doubled, obviously the number of moles is also doubled. Okay. And weight of the solvent is half. Now that means this becomes 1/2. Okay. So now what is going to happen? We are doubling this and we're making it half. So this 2 goes up. So can I say that overall this is going to become 4 times? Right? Overall it is going to become 4 times. Is it not? because this we are half, they're making it half, and this we are doubling. So this 2 also goes up. So 2 into 2 will become what? 4 times. So this thing of the solution is going to be 4 times the initial value. That is what is going to happen to the boiling point. Okay, I hope you're getting the answers, right? Okay, next question. Why is the, I think this is freezing point, right? Freezing point depression of 0.1 m sodium chloride is nearly twice the value of 1 m glucose. We already saw this. Why? Because why? Why is it the freezing
Sodium
point depression?
chloride has Van factor. Here it doesn't.
Because sodium, you should not write sodium chloride as Van factor. You should tell that sodium chloride undergoes dissociation. So that makes the colligative property also to be higher. And then you can write about the Van factor. Obviously, you can write in terms of formulas. Pi is equal to I into C into R into T for sodium chloride, whereas pi is equal to C into R into T for glucose. That also you can write. Okay, right? Moving on. Okay, I think that's it. We are done with all the questions. Amazing, amazing. Right? Okay, any particular question you have to ask me? Okay, fine. Let us stop right here. Right? And thank you so much. We'll meet again next week. Right? I'm ending the class.
Thank you, sir.
Thank you.
Thank
Thank
you,
you,
sir.
sir.
Thank you, sir.
Thank you, everybody. Thank you.